Hello all, welcome back to Regression and Classification course. This is lecture 4. We will start with a basic simple models with empty cars dataset. So in this empty cars dataset, our target variable is miles per gallon, and we are trying to fit essentially the weight on the x-axis and miles per gallon on the y-axis. So the model that we are fitting is miles per gallon as a function of weight. So miles per gallon equal to beta naught plus beta 1 times weight. So beta naught will be the intercept term. It will be the intercept term, and beta 1 is the slope. So we have some kind of line, that is what we will try to fit in this model, with this model. Now this model, as we have seen in the previous previous lectures, that can be defined. These models can be defined using the matrix notation y equal to x beta plus epsilon, where my y is a vector of n dimension, miles per gallon 1, miles per gallon 2, miles per gallon n. So we have n samples. In each samples we have about like miles per gallon. Now what we have is x has two columns. The design matrix x is the typically called design matrix, and the first column all ones. This first column with all ones represents the beta naught, and the second column is weight, that is the weight of the independent vector. And then the beta here have two parameters. We want to estimate beta naught and beta 1, and the epsilon here, my epsilon has n elements, epsilon 1, epsilon 2, epsilon n. Okay. Next, what we can do, we have seen that in normal equations will give you, this is the analytical solution, x transpose x inverse x transpose y. Now in the x is, we have defined, this is our x, this is our x. So all you have to do, just write x transpose x, and if you do x transpose x, that will give you this matrix. The first element is n, second element is sum of the weights, and this is sum of weights, and this is sum of weights square, and this is same as this one because this is essentially symmetric matrix. X transpose x is going to be your symmetric. Now this is your x, this is our x transpose y, this is our x transpose y, and this is our x transpose x inverse. Okay. Now next, what we are going to do, we already had beta naught plus beta 1 times weight. Now we are going to add a third second independent variable, not third, second independent variable. So this is miles per gallon is our target variable or dependent variable. First independent variable that we consider in the model is weight, and the second independent variable we are going to consider is the displacement. Now, if you do that, essentially the geometry will look somewhat like this. So previously we were essentially considering weight on the x-axis and miles per gallon on the y-axis. Now we have added a z-axis. Here we have added a z-axis. This z-axis is displacement. A new variable is being brought. So the points which were previously on the 2-dimension, you see these are the points. Now each of the, say if you take these points will be typically, suppose this is the ith points, it will be like MPG I, WTI. It's a tuple of 2-dimension. Now what we have is essentially a third variable, and if this is the point that we were talking about, this point is MPG ith value, WTI, and displacement is the third value, displacement of the ith sample. Now that means this is on the third dimension, and hence the entire geometry is in the third dimension. In that third dimension, we are trying to fit this model. This means this model is actually fitting a regression plane. Or simply 2D plane. So in a 3-dimension, the data set is in a 3-dimension, and we are trying to fit a 2D plane. So data is in 3-dimension, and we are trying to fit 2D plane. Okay. Next, how can we write it in matrix notation? So we can take this model and we can write it in matrix notation. That if we can write it in matrix notation, that will clarify our concept more clearly. So we can write this one using y equal to x beta plus epsilon. Y is as usual all the miles per gallon vector of dimension n, and now this is what we have, the design matrix. Previously we had the intercept column and weight, and the third column in my design matrix is displacement. In the intercept, the regression coefficient has now a third parameter, beta 2. So previously I just had beta 0 and beta 1. Now we have beta 2. The residual vector is as usual epsilon 1, epsilon 2, epsilon n. Now if we solve this as a normal equation, so it will be x transpose x inverse x transpose y. So here is a ask yourself question, how the analytical solution of x transpose x inverse x transpose y would like. So if you remember, for 2-dimension, for the previous problem, we solved this, and this was our solution, right? This was our solution. This was our solution. Can you develop the solution for the two-dimension case? Can you develop the solution for this case, this model? So this is my question. This is my question. So what I'm going to do, I'm going to request you to stop yourself and for about 2 to 5 minutes, pause your video, think about it, how you can solve this. Okay? Now, let us come back. I hope you have tried and you have the solution. So let us see how the solution would look like. It is slightly cumbersome, but we can figure it out. So you can see this first will be n, second will be weight, summation of weight, third will be the summation of displacement, then this will be again the weight square and displacement square, and this will be cross product of weight and displacement. So this matrix is the X transpose, this matrix is X transpose X. You have to take the inverse of that, and this matrix is your X transpose Y. So the first element is simply sum of weights, sum of miles per gallon. The next is weight times miles per gallon, and the third one is weight times displacement. I hope your answer was correct. Next, we will move on to a new topic called quadratic regression. In quadratic regression, what we will consider now, in the same data set, miles per empty cars data set, we have miles per gallon and horsepower. In the miles per gallon and horsepower, what we are doing, we are plotting the horsepower on the x-axis and miles per gallon on the y-axis. We could have easily fit a straight line here, but looks like one can try also the quadratic regression. Now, how this quadratic regression can be fit? The simple way of doing it, miles per gallon as a function of beta naught plus beta 1 horsepower plus beta 2 horsepower square plus epsilon. Now, this horsepower square is a very interesting term. Let us try to understand what are we doing adding horsepower square. So essentially what we are doing, this was our original two-dimension plot, horsepower on the x-axis, miles per gallon on the y-axis. Then we are putting horsepower square on the z-axis. This is our horsepower square. So we are creating a third dimension. So horsepower, this is our third dimension. So our original data was on the two dimension. This is the original data is in the two dimension, right? Now what we are doing, we are creating a third dimension horsepower square, and by doing that we are putting the two-dimensional data into third dimension. We are putting it into third dimension. Now, how can we model it? Simply what we are doing here. So this is my model. This is our model, right? We can write it in y equal to x beta plus epsilon. My y is exactly same. So the first is intercept column, second is the horsepower, and the third column we are creating a new column, called horsepower square. We are engineering this new column. Okay, and rest of the thing is as usual previously. So beta naught, beta is my regression coefficient, which has 3 parameters, and epsilon, bunch of epsilons that we have here. These are n dimension epsilon. So the linear model is actually linear in parameter. When we call a linear model, it's not necessarily it is linear in predictor or linear in variable. When we call it as linear model, by saying linear model, we mean it is linear in parameter. So how can we solve this quadratic regression? Same way, x transpose x inverse, x transpose y, and you can solve this by yourself. This is your x transpose x, you have to take the inverse of that, and this is your x transpose y, and then if you solve these two, multiply these two matrix, what you will get? Your beta hat. So, and if you do that, you will fit a plane. So what is it actually what we are doing? So essentially my data is in the two dimension, in the x-axis and y-axis. We are engineering a new axis called horsepower square. And then what we are doing is essentially fitting a hyperplane in the 3 dimension. This model is a 2D plane in 3 dimension, but quadratic in 2 dimension. And this is how are we achieving this? By engineering this new feature. This is new engineered feature. In machine learning, it is called feature engineering. In machine learning, it is called feature engineering. In statistics, it is same thing. It is called variable transformation through basis expansion. And we will talk about it, the both thing. But essentially we are creating a new variable, and that's why it is called variable transformation or feature engineering. So feature engineering or variable transformation, what we are doing, we put the original data into higher dimension. So this is the first trick. The trick is we put the original data into higher dimension. And you hope that we will find that a good fit for a linear hyperplane in a higher dimension, and which will explain the nonlinear relationship between the feature space and the target variable. So if I go back in this example, so clearly in this example, the relationship between horsepower and the miles per gallon is not really a straight line. It's not linear. It looks like they have some kind of a non-linear relationship. And if they have a non-linear relationship, then it is better we should use the feature engineering technique. And what we are doing, we are creating a new dimension a new dimension. We are by creating featuring with the feature engineering, we are putting the two-dimensional data into high dimension, into 3-dimension, and in that 3-dimension we are trying to fit a hyperplane, in this case 2D plane. But fitted 2D plane, this fitted 2D plane is essentially a quadratic regression for this is the model. Remember that this 2D plane, this quadratic regression is actually a 2D plane in 3-dimension space. Now we are generalizing this concept, I just spoke to you regarding the quadratic regression, that yi fxi plus epsilon I. So there is some relationship between yi and xi. I is the ith record of the data set, and we suppose we can write this f of x as summation beta j phi of xj. So phi is basis system of the f of x. So that means we can write it as phi of beta. So this is how we can typically write. So what is the example? The example is, if we take this simple quadratic regression type thing, so we can generate a generic terms of curvature in linear regression. So we can just say y equal to beta naught plus beta 2x plus say beta 3x square plus beta 4x cube. So basically higher order polynomial. So this is a polynomial, right? So you can fit a polynomial, and this x square, x cube, these are the basis of the polynomial. In machine learning, this phi or the basis is known as engineered feature, and the process is known as feature engineering. Now, if you have a function which is very sinusoidal in nature, you can define a function like beta naught or beta 1 plus beta 2 sine omega x plus beta 3 times cos omega x plus beta 4 times sine 2 omega x plus beta 5 times cos 2 omega x, and you can go on as you want, as many Fourier as you want you can consider, plus epsilon. Now consider omega 2 pi by p. It defines the period. Suppose this is where a period starts and this is where a period stops. So this period is our p. So defines the period p of oscillation of the first sine cosine pair, and p is known. We are assuming p is known, otherwise this unknown p will create some problem. For the time being, we are just assuming the p is known, and for many examples, for many real life examples, p is indeed known. So our basis system is phi, and beta is beta 1, beta 2, beta 3, and you can effectively write y equal to phi beta plus epsilon, and this phi is, as discussed, is known as the engineered feature. Now you can define a model, no harm, MPG equal to beta naught plus beta 1 sine omega hp plus epsilon. So you can always define a model like that, and you can try out whether it's good fit or not. So we are writing the function with its basis expansion. We call it phi y equal to phi beta. Let's assume these bases or the engineered functions are fully known to us. Okay, so this is something we are making this assumption. This phi system is completely known to us, and the beta is unknown. So beta is completely unknown, and what we want to estimate beta. So we want to estimate beta. So this comes into the something called functional estimation or functional learning. We'll talk about it more into the later. So we can apply here also the OLS estimator. There are different method of estimation for beta is there, and we can simply apply the OLS estimation of phi transpose phi inverse phi transpose y. We have done that same for the quadratic regression. Now, question is uncertainty associated with this OLS estimator. How do we estimate the uncertainty, or that is margin of error associated with the OLS estimator beta hat? So if x naught is a test point, you plug the x naught here, okay, you take the beta hat and you got the y hat. So y hat is the predicted value, but the true y naught is unknown. The true y naught is unknown. So what is the margin of error of y hat? Can we say anything about the margin of error of y hat? And if we can say something about the margin of error of y hat if we have some idea about the beta hat. If we can say something about the beta hat, then only we will be able to say something about the y hat. So with this, we will stop and we will move on to something called the sampling distribution and the inference of the regression coefficient. So the sampling distribution will give us that how much margin of error you can expect along the beta hat or your predicted y hat. So in the next video, we will resume with the sampling distribution of beta hat. Thank you very much. See you in the next part.